Good evening, everyone. Myself Sana Sheikh, a second year PhD student at IIT Bombay, and I'm a TA for the course NPTEL course named Symmetry, Stereochemistry and Applications, and the course instructor is Professor Anshuman Roy Chaudhary from IISER Mohali. Today we are going to discuss the previous year week 7 question. So in this live session, always on Monday from 7 to 9 p.m. we are discussing the previous year questions. So this is the 7th week. So we are going to discuss the 7th week previous year question. So today's topic is SN1 SN2 mechanism, and we have to find out the reaction possibility according to the different nucleophiles. So let's start the session. So before starting the question answer session, I would like to give a brief introduction about today's topic, that is SN1, SN2 even and E2 elimination reaction. So what is SN1 reaction? SN1 reaction have two or more steps involving carbocation intermediate, and it's a first order kinetic reaction, and the substrate dependency is on uh, from carb is the substrate dependency is based on a stability of carbocation. Tertiary carbocation are more stable and primary are least stable. And the stereochemistry obtained by this reaction is racemization, means both the product possibility is there, and uh, this is not involved in RDS but less basic from nucleophile while limit E2 elimination. So this reaction involve rate determining step as a first step, and it competes with even and E2 elimination reaction. What is mean by compete means with the SN1 product there are possibility to get the even and E2 product also, and this is more favorable in polar protect solvent. While talking about the SN2 reaction, it's a one-step reaction and biomolecular reaction, because the rate determining step is rate is depend on both the concentration of alkyl halide as well as the concentration of nucleophile. That's why it's a biomolecular reaction, and it's a second order reaction. First in substrate and the second is nucleophile. As I told you, it's depend on the rate is depend on both the concentration substrate as well as nucleophile. The substrate dependence on is based on the re- on the uncluttered the reaction, that means the steric hindrance of the reaction. I will discuss in later in slide, then it will be more clear to you. For right now you just remember the steric hindrances matters in SN2 reaction. So it should be a good nucleophile which is involved in the reaction. Now in SN2 reaction we are getting specific specifically one product, that means it is a stereospecific inversion. Now the in this reaction reactivity of nucleophile is very important, since it is the rate determining step is involved concentration of nucleophile. That's why its the reactivity of nucleophile is very important here. Whereas in case of SN1 it was not that much important. It was the reaction rate was depend on only the concentration of alkyl halide. That's why in SN1 reaction it was nucleophilicity was not matter that much. But here in case of the SN2 reaction, reactivity of nucleophile is very important, because it involved in the rate of reaction. Now uh, in involved leaving group is involved in RDS, so it is also important, and it is compete with the E2 elimination reaction when basic nucleophile was employed or used. And SN2 reaction is more favorable in polar aprotic solvents. And now let's talk about the even elimination reaction. E means elimination reaction, S means substitution reaction. Remember this one. S means substitution, N means nucleophilic, and one is unimolecular, and two is bimolecular. Similarly, in case of E1 and E2, E1 is elimination, unimolecular elimination, and E2 is elimination reaction with bimolecular process. So here we have even elimination. So even elimination mechanism is based on two or more step involving carbocation intermediate. same as SN1 mechanism. In SN1 also we have two or more steps involving carbocation intermediate, same in case of E1 also. Now the E1 and SN1 have mostly have a similarity. As you can see here, the kinetics is also depend on the first order in substrate, same as SN1, and the substrate that are formed are based on the stability of carbocation, same as the SN1 reaction. And in this case also we are getting mostly a mixture of two compounds. Now, here, if a good or non-basic nucleophile is present in the even mechanism, then SN1 will be favorable. So, even is always competes with SN1. We will discuss later. So, it involves the RDS, so it is important. Nucleophile leaving group is involved in determining step. Similarly, in case these two cases also SN1 and SN2 also. Now, as I told you, it competes with SN1 means sometime along with the even elimination reaction, we are getting product of SN1 reaction also, and it is favorable in polar protic solvent. Now, what is E2 elimination? So, it is same as SN2 mechanism. So, it is one step biomolecular process, and it is a second. The kinetics of the reaction is depend on the it is a second order reaction, and first in substrate and base. So, that means it is the rate is directly proportional to the concentration of substrate and base. In SN2 it was depend on substrate as well as nucleophile, so here it is depend on base. It requires a strong for E2 elimination it requires a strong base and any substrate with beta proton. We will discuss what is beta proton in later. So if talking about stereochemistry, it is a stereospecific reaction and anti-periplanar relationship of beta proton are leaving group. We will do the examples. Now, let's talk about the importance of base and nucleophile. So, in this E2 reaction, non-nucleophilic bases and strong bases are the best for SN2 mechanism. So, it competes with SN2 mechanism. That's why all the similarity are there with SN2 reaction, substitution reaction. So, because leaving group is again involved in the rate determining step, so it is important here. Now, the solvent is varies depending on the reaction in E2 mechanism. Okay, so this is a small view of the basis used for such type of reactions. So I hope you will observe this type of reactions in a lecture which are available on YouTube by Professor Anshuman Roy Chaudhary. So you can view these lectures based on this topic. Now we are talking about the questions. The question number 1 is arrange the following molecules in the ascending order of substitution reaction by SN1 pathway. Means we have to arrange these substrate in a ascending order, means from lowest to highest SN1 reactivity. So can you tell me about the reactivity of these compounds? Anyone? What is A? Phenyl group is there. I will draw here. Okay, this is a phenyl ring. This is carbon atom which has two substituent. One is methyl The other one is hydrogen and chlorine. Correct? Now this is a. What is B? Whenever you are facing the problem with these type of compound, you have to write in open form. Always write in open form any compound, then it will be more clear to you and it easy to understand. So always write in this form. Then it will be easy to compare these compounds. That's why I'm writing this way. This is carbon only. What is the third one? C. Hydrogen, hydrogen and Cl. And last one is D. What is this? Cl, CH3, CH3. Okay. Now let's talk about the first example. As all of you know that SN1 pathway is always based on a carbocation formation, as we have discussed earlier, and in lecture also sir has explained very well. So please go on YouTube and watch those videos and it will be more clear to you. So here as you can see, halogen chlorine is a living group. If it will leave here, the compound it will leave here, what will happen? Carbocation formation will take place. Correct? So I will write here what will happen? Carbocation formation. Correct? So as a stability of carbocation enhance the rate of reaction for SN1 pathway. As all of you know that stability of carbocation increases the SN1 reactions pathway, reactivity of SN1 reaction. Okay. So let's draw the carbocation for all the structures. So which carbocation is more stable? Anyone? If we will talk about the carbocation stability, the tertiary carbocation are the most stable carbocation because the positive charge is stabilized by electron donating group present in the molecule. That's why the tertiary carbocations are the most stable carbocations, and the primary carbocation is a least stable carbocation. Sorry for the mistake. This is CH3 only. I have drawn the butane. So this is CH3. Okay. Now this is the primary carbocation. The last one is the primary carbocation. As I told you, the stability pattern according to that way, this is the least stable carbocation in this group. Least stable primary carbocation. Right? Stability is lower than the secondary one, correct? This is the secondary carbocation. Secondary. This is the primary. And this is the tertiary carbocation. Sorry, this is also the primary carbocation. Because it's present on this position, but it is a benzylic position. Benzylic position. And when we'll talk about this one, this is the secondary carbocation. This is the primary carbocation. Correct? Now, here you can see that the carbocation have here two groups, methyl and phenyl group. So it is comparatively stable than this one because it has only phenyl group. It is primary carbocation, but it is stabilized by this phenyl ring also. But here you can see that all three substituents are present on carbon is hydrogens only. So this is the least stable. Then this is the stability will be like this. This is the less stable than tertiary one, and the secondary one is less stable than the tertiary one, because as I told you, the tertiary carbocation are the most stable carbocation. So what will be the pattern for this one? What will be the pattern? See, B is the highest high if we are talking about the SN1 pathway, highest means most stable carbocation is B. That means it will follow the SN1 pathway substitution reaction. So this will undergo the very quickly in a SN1 pathway reaction. So this is if I am talking about ascending order, then the least one will come first. So D is the least one. D is the least one. Correct? Then C is the second last. C, correct? Then A, because A is a secondary carbocation, that's why A. Then the tertiary carbocation will be come in last. So this is the order it will follow. Understood? This is the ascending order of substitution reaction by SN1 pathway. I hope all of you are understood. Let's talk about the second example. Here, now I hope all of you are getting the concept behind the SN1 reaction, SN1 pathway. So first is SN1 reaction is based on the stability of carbocation, and the second thing is that SN1 reaction pathway is based on the uh, leaving group uh, present in the molecule. So ability of the or the tendency of the leaving group is also matters in the SN1 pathway. So as we are moving from uh, right to left in periodic table, basicity increases and nucleophilicity is also increases. Similarly, in case of the uh, row, here we are talking about the row. Now, similarly, in case of the group column, from from low downside to upside, the basicity is increases and wait, as the size increases downside, the basicity is decreases. Basicity is decreases. Correct? And if you are talking about in same manner, then I can show this in a upward arrow. That means the basicity is decreases from top to bottom, or we can say top from bottom to top, the basicity is increases anyway. Okay, so when I will write here, all the molecule have same similar structure here. CME twice is similar here. Correct? CME twice is similar in all the cases. Methyl, methyl, hydrogen, and halogen is fluorine, bromine, chlorine, iodine. So fluorine is the most basic one. As I told you, from top to bottom, the basicity is decreases. So fluorine has the highest basicity in these halogens, and iodine has the least uh, lowest nucleophilicity or basicity, we can say. So according to this one, the most stable carbocation formation will be done by most basic halogen attached to the compound. So here you can see that iodine is good leaving group, but the fluorine, because it is a SN1 pathway, it is we are uh, writing in SN1 pathway. That's why it is it will be inversible. Like I will tell you. See here. If we will talk about SN2 reaction, what SN2 reaction is one step reaction. Bond making and bond breaking is takes place simultaneously. So in this case, if iodine is but iodines have a bigger size compared to fluorine one, correct? Iodine size is more compared to the fluorine one. So it's a good leaving group. So when the nucleophile attacks here, then because it's good leaving group, it leaves easily. But in case of SN1 pathway, what happens here? First carbocation formation is takes place, then the second step is a nucleophilic attack. So here in this SN2 reaction, iodine have a highest rate of reaction. The molecule with iodine will show the highest rate of reaction, then bromine, then chlorine, because these are good leaving group, then chlorine. So here also, in this case also, because fluorine is a good leaving group, but not that much as iodine has. So iodine is a good leaving group, so it will form easily carbocation. The carbocation formation here will be easy for this group. Carbocation formation will be easy. So that's why the the second step will be easy to occur here. So because the rate of reaction is based on first step in this SN1 pathway, so the first step have good leaving group, so it will be more feasible. So this is the highest, this molecule will show the highest rate of substitution reaction with SN1 pathway. Now let's talk about the second one. So second one is with bromine. With bromine. SN1 pathway is also based on solvent also. So the polar protic solvent favor the SN1 pathway, as we have discussed earlier. But here in this example, we have to focus on leaving group only. It's depend on leaving group. Okay. Methyl. Sorry. Here we have proton. Then chlorine. Correct. So this is the order it will follow. So because it's at ascending order, so A will be first one because it will uh, among these molecule it will show the least uh, feasibility of SN1 pathway. Then C, then B, and last D. Correct? Got it? Okay. Now let's move to the question number 2. Yeah. So in this question, the question is predict the products of the following reaction. What will be the product for the following reaction? So here we have two conditions, two different conditions. OH minus is a nucleophile also, H2O is a different nucleophile. So there are two different conditions. First with OH minus we have to write the reaction with OH minus. Because OH minus is a strong nucleophile, some counter ion is also present which is not written here. NaOH or KOH or LiOH, lithium hydroxide, sodium hydroxide, potassium hydroxide, any base, or we can say OH is a very good nucleophile compared to the water. So if the reaction perform under the strong nucleophile, the product will be SN2 reaction product. The reaction will follow the SN2 mechanism. That means a biomolecular reaction. That means the bond breaking and bond making process will take place simultaneously. So what will happen here? We have halogen iodine as a leaving group. So the product for the first step means with this strong nucleophile will be SN2 mechanism product. I will write here what will happen. Any guesses? Any guesses? Yeah. OH will attack over here this carbon because this is a primary carbon atom, and this halogen because two hydrogen group are present on this carbon atom. So it will the SN2 mechanism is favorable with strong nucleophile. So the iodine will leave, and the bond breaking process will take place simultaneously, and exclusively we will get this product as a uh, stereospecific product. In this case the stereochemistry will be inverse. Here it is in this starting material the stereochemistry is not mentioned. That's why here also I did not have mentioned the stereochemistry, but in other cases where the stereochemistry is mentioned, we have to show the inversion of nucleophile group present on the starting material or the compound. So this is the first product with OH minus nucleophile. Now let's talk about the second reaction given in this same question. This is with H2O with water. So if the reaction will be done by water, it will undergo SN1 reaction because water H2O is a more weak nucleophile compared to the OH minus. It's a very weak nucleophile. OH2 H2O is very weak nucleophile. So it will follow SN2 mechanism. Sorry, SN1. This is the SN2. Okay, this is SN1. So according to the SN1 mechanism, what happens first? As all of you know that SN1 mechanism is based on two reactions. That is stability of carbocation. So here the carbocation formation will take place. So first talk about the carbocation. SN1 pathway is the rate of SN1 pathway is depend on the concentration of substrate only, or we can say alkyl halide. when this leaving group will leave, so the carbocation formation will takes place. So here we will get the primary carbocation. As all of you know that the secondary carbocation is more stable. So what will happen? The SN1 migration will takes place. Migration of this CH3 group will takes place here. So after the migration, what will happen? Carbocation will generate on this carbon. Because carbocation wants stability, that's why the migration is taking place. So here what will happen? CH2, CH3, correct? Okay. Now nucleophile will attack on this carbocation and the product formation will takes place here with this one, this way. So this will be the SN1 pathway product. This is the SN1 pathway product. So the same with same substrate, if we will perform the reaction in with strong nucleophile, we will get this product exclusively, stereospecific product. And if we will perform the reaction in the presence of H2O, which is a weak nucleophile, we will get this product as a major product. And in SN1 reaction, what happens? We are getting a racemic mixture, means the stereochemistry of this OH will be front side as well as back side. It's not depend on the substrate, because after the carbocation formation, nucleophile can attack from both the side, from bottom as well as from top side. That's why we are getting racemic products, not stereospecific. Okay. So these are the possibility of product in this case. Now move to the next question. Yeah. On arrow you can see here only H2O is given. That means we have to consider H2O as a nucleophile here. Only H2O is given. So here you can see that this is a cyclohexane, di-substituted cyclohexane. This is the halogen group present on dash position. So what will happen? Because H2O is weak nucleophile, as we have discussed earlier, it is a weak nucleophile. So a weak nucleophile means it will follow the SN1 pathway. For SN2 pathway, a strong nucleophile is required. Here we have weak nucleophile, that means it will follow the SN1 pathway. So what will happen first? First the carbocation generation takes place. Then the attack of nucleophile will be done on the substrate. So this will remain as it is, correct? This is methyl. And here we have carbocation formation. So after the carbocation formation, what will happen? Nucleophile can attack from both the side, top as well as bottom side. From top and bottom side, as both sides are available for the reaction. So we will get the racemic mixture. Racemic mixture. Correct. So in one case, what we will get? Hydroxy group above the plane. And the second possibility is there with hydroxy group below the plane. Because weak nucleophile is present, that's why it will follow SN1 pathway. That means first bond breaking will takes place, then bond making. Okay, these two are the product for this reaction. Sorry. and this is the intermediate. Correct? I hope this will be clear to you. Now let's do the third example. Yeah. So here two conditions are given here. So we will discuss each one by writing the intermediate as well as product. Each and every one we will discuss here. So here first we will discuss OH minus, that is strong nucleophile. So in the presence of OH minus or strong nucleophile, what will happen? As I told you, it will follow the SN2 pathway. This is not hydrogen. Mistake has done here. This is not hydrogen. It is halogen. Any halogen. Consider this one as an any halogen. I am writing this one as a Br. Consider it's an Br. Okay, bromine. Now, what will happen in presence of strong nucleophile? The bond making and bond breaking will occur simultaneously. That means here it will go like this, and OH will attack on other side. OH will attack from one side and bromine will leave from other side. Okay. So the from front side, as you can see here, Br is present on back side of the plane, below the plane. So front side is free and OH will attack from the front side. Okay. So what will be the product here? It is stereospecific product, and we will get only one product by SN2 mechanism. But the inversion of stereochemistry will be observed here, as I told you, because the bond making bond breaking is happening simultaneously. That's why the inversion is observed, because from one side nucleophile is attacked and from the other side leaving group is leaved. So this will be the product for SN2 mechanism. SN2 mechanism with strong nucleophile. Strong nucleophile. This is stereospecific product for first condition. For this condition. Now, the second condition is H2O. As in the second condition, H2O is used as a nucleophile. So, what will happen? It will follow the SN1 pathway. That means first bond breaking, then bond making. So, let's write down the product here. This is with H2O. Correct? What will happen first? This leaving group will leave and we will get the carbocation formation in intermediate. Carbocation formation will take place here. Okay. So carbocation formation takes place here, and after carbocation formation, nucleophile will attack. Nucleophile, which is our water, okay. So here the formation of, after the formation of carbocation, nucleophile will attack from both the side. The possibility of nucleophile to attack from both the side is there. So from front side also it can attack, or it can attack from the bottom side. Okay. So we will get racemic products, two products. One with the stereochemistry upside, sorry, OH front side, and the second possibility is there with below the plane. OH will go below the plane, correct? Methyl group. So these two products are possible with SN1 pathway. So for with first reagent with a strong nucleophile, we will get only one product, that is the with inversion of nucleophile or stereochemistry, inversion stereochemistry. And in case of SN1 pathway, H2O is used. In presence of H2O, it will follow SN1 pathway and it will give racemic product. Racemic product. So these are the products possibility for this reaction. Racemic. Okay. I hope all of you are clear. Now let's move to the next example. Yeah. What is this? Again the cyclohexane with halogen substituted cyclohexane. So here also we have two conditions. One with strong nucleophile and the other one with weak nucleophile. OH is strong nucleophile and water is weak nucleophile. So first we will discuss the strong nucleophile reaction, then we will discuss the weak one. So if the reaction will take place in a presence of OH minus, it's a strong base and nucleophile. So in presence of OH minus, it will follow the SN2 pathway. Yeah, here you can see OH is strong base, correct? Strong base and good nucleophile. So if we will write the starting material or a compound, a molecule in a chair form, then we will observe that it is a cis isomer, right? Cis isomer. So this OH minus will attack from bottom side, because the bottom side is more less hindered and more available for the substitution, and it will the bromine group will leave from here, it will leave from this side, correct? So strong because the bond making, bond breaking will take place simultaneously in SN2 pathway, so we will get this as a product, right? This is the product possible for this reaction. Now let's talk about the elimination reaction product. If as I told you in first slide only, that SN2 pathway is competes with the E2 elimination reaction. So here you can see that E2 elimination is possible here with this proton. Suppose I will write here this way. This is bromine. This is methyl. Sorry. This is methyl. So what will happen? Here we have two hydrogens. One is back of side of the plane and one is front side of the plane, correct? So the elimination is always happen anti-periplanar. Elimination is done on as anti-periplanar. So bromine is on front side and the anti-periplanar hydrogen with this bromine is this one. this one, correct? So because anti-periplanar hydrogen is present, the elimination will take place and we will get this product. This product. The mechanism will be like this. So the elimination will take place. That is because OH minus is a strong base. It will abstract the proton, this one, and then the Br is good leaving group and it will leave here and we will get double bond over here. Double bond. Now the second possibility is there, because as I told you the anti-periplanar elimination is taking place in A2 elimination reaction. So backside we have here, on this carbon atom backside we have hydrogen, which is anti-periplanar to the bromine atom, correct? Bromine group is anti-periplanar to this proton. That's why it is also possible. So it will eliminate this way. The proton will be abstracted by strong base and the followed by elimination of leaving group results in a double bond formation. So this is the product possible for this stage. So these are the two products obtained by E2 elimination reaction. So in this example there are three possibility of three products. For one is with SN2 reaction pathway and the two other products are from E2 elimination reaction. So I hope all of you are clear with the products in this case. Let's talk about the next one. Yeah. What's the difference between these two? In this case, in previous one it was cis and in this case it is trans, as you can see here. So again we have two reaction condition. Here I did not have discussed the second condition, sorry. Now with the second condition we have water. So in case of this weak nucleophile, what will happen? It will undergo SN1 pathway, correct? SN1 pathway. So carbocation formation takes place here. Okay. As I told you, after carbocation formation, nucleophile will attack from either back side or front side. So because carbocation stability is matter in SN1 type reaction, what will happen? The proton of this carbon will migrate here. A rearrangement will take place. Will migrate here and we will observe the tertiary carbocation formation. Formation of tertiary carbocation. Which is more stable compared to the primary one. Okay. So what will happen here now? The nucleophile will attack from back side because only below the plane is available. Back side of the plane is available for the attack. Methyl and OH. Okay. So this is the product with SN1 pathway. So this is the second example. Here we have trans isomer of the previous example. So this is the methyl bromomethyl cyclohexane example. So in this case again we have OH and H2O as a nucleophile. So in first case we have hydroxy group as a nucleophile, OH minus is a nucleophile. So it's a strong base and a strong nucleophile. We have OH minus. It's a good nucleophile. OH minus is good nucleophile. Okay. So here what will happen? It is because as in SN2 pathway, bond breaking and bond making is happens simultaneously. So Br is a good leaving group. Nucleophile will attack from backside, and we will get the product this way. But this is not much more feasible because of the presence of this methyl group. It will create a hindrance, and nucleophile will the rate of reaction will decreases because the nucleophile is um, face the steric hindrance because of methyl group present on below the plane side. So this is the SN2 pathway possibility, but the A2 elimination will be favorable for this type of reaction because of the steric hindrance. So what will happen? Instead of the nucleophile attack, this is the SN2 product, possible product, but this will be the manner one. This will be the manner one. The major product obtained with a strong nucleophile in this reaction is E2 elimination product. What will happen? Bromine will leave here from here because it's a good leaving group, but the proton present anti-periplanar to this bromine group will also leave, and it will form double bond here. Double bond here. It will leave. Okay. The strong base will abstract this proton, which is anti-periplanar to the leaving group, and it will give the double bond formation in a product instead of nucleophile attack. So here OH minus will act as a strong base, not as a nucleophile because of the steric hindrance. So this will be the major product in case of strong nucleophile. Case of strong nucleophile. Is it possible in another way? No. Why not? Here, as you can see that here we have both the protons, front side as well as back side, correct? So the proton which is anti-periplanar to the bromine can leave from here, correct? But in this case, the other way, the proton is present on front side of the molecule. Yeah, front side of the molecule. You can see here it is present front side, correct? So it is not anti-periplanar to the leaving group because the elimination is done by the anti-periplanar proton only. That's why this is not possible. So that's why we will get only one E2 product. In previous case we got two E2 product because of the anti-periplanar proton present on the tertiary carbon also. That's why we got two E2 elimination products, but here we will get only one E2 elimination product, and SN2 product will be the lowest priority, means the least feasible. It's a least feasible reaction because of the presence of methyl group below side. So this is the reaction with OH minus. Now let's talk about the reaction with weak nucleophile, that is H2O. So again the carbocation formation will take place with H2O. Here I am writing with H2O. Reaction with H2O, weak nucleophile. Okay. Here what we will get? Carbocation formation, right? As we have discussed in previous case, the carbocation stability the carbocation stable on tertiary carbon atom is more favorable and more stable. So the tertiary because of the stability of carbocation, the migration of proton will take place. Migration of proton will take place, and we will get the tertiary carbocation. Tertiary carbocation. Okay, so here again the possibility is there. It can the nucleophile can attack from front side as well as from back side. So here we will get the two different products with SN1 pathway. The one is front side attack, OH, and because here is not the possibility for the front side back side attack, because methyl group is present on back of the plane. Sorry for this one. Here, yeah, here both the possibilities are there. Sorry. In previous case also, both the possibilities are there in SN1 mechanism, because after carbocation formation it will become planar and then it can attack from any side. Yeah. Stereochemistry will not remain same after carbocation formation. That's why you will get both the product. Yeah. It will become planar. In this case also, yeah. What's the other product formation will take place? Back side of the plane. Okay. These two are possibility for the SN1 pathway mechanism. But as I told you, SN1 pathway is competes with even elimination reaction. Because of the hindrance, it can undergo even elimination reaction. And with even elimination reaction, what will happen after carbocation formation? This is SN1, right? Yeah. After carbocation formation, the nucleophile will or a weak base will abstract the proton from any side, right? Will abstract the proton and the double bond formation takes place with elimination reaction. So this will be the product by given elimination reaction. Done. So here four type of reaction are possible with strong nucleophile SN2 and E2 elimination will take place, and with weak nucleophile even an SN1 reaction will take place, and we will get different types of products. In first case we will get two products, one with SN2 reaction and one with E2 elimination. In the second case with weak nucleophile we will get the three product. SN1 will give the reciproc products and even elimination will give this alkene product. Clear? Okay. Now this is the third example. So here again we have the two reactant. So first we will discuss with the reaction with the sodium methoxide. Then with methanol we will discuss. So first reaction I am writing with sodium methoxide, with only sodium methoxide. What will happen? Yeah. Here you can see that this is secondary allyl halide, right? This is secondary alkyl halide, and when we are treating this with a methanol, yeah, I'm talking about first reaction condition first, then we will talk about the second one. Okay, so when we will treat this with a sodium methoxide, which is stronger base and good nucleophile. So what will happen with stronger base and good nucleophile? It will follow SN2 pathway. I already told you it will follow SN2 pathway because it's a strong nucleophile and a strong base, good nucleophile. So the bond making and bond breaking will take place simultaneously, and it will attack from backside. This OMe group will attack from backside. Sodium is a counter ion only, so the nucleophile is OMe. OMe is our nucleophile, so it will attack over here, and it will leaving group will leave from here. So the bond making bond breaking will take place simultaneously, and we will get stereospecific product, that is backside substituted OMe group product. This will be our SN2 product. Instead of SN2 reaction, it can also follow the E2 elimination reaction. So when it will follow the E2 elimination reaction, what will happen? There are two possibilities. One is that it can abstract the nucleophile base can abstract this proton, and it will give double bond over here. Yeah, this way. And leaving group elimination of leaving group results in a formation of one E2 elimination product. The other possibility is that it can abstract the proton from this primary carbon atom, and it can give a other E2 elimination product. In these two products, this product will give the more yield, or it's called, we can call it is a major product, and the second one will be minor one. Why? Because it will follow the Setzap rule, and this product is followed by Hoffman rule. So according to the Setzap rule, this product will be the major one because it is thermodynamically stable reaction. Thermodynamically favorable reaction is Setzap reaction, and it will give a major product. Okay, so in this reaction, here these three type of product formation is takes place. Three product formation will takes place. Okay, now let's talk about the second condition with methanol. Okay, with methanol, what will happen with methanol? When the same substrate will be treated with methanol, their R is methyl group only. So methanol is a weak base and a poor nucleophile, and it is a polar protic solvent. It is also a polar protic solvent. Then that means it will favors the SN1 mechanism reaction, because the SN1 is favorable in polar protic solvent. The previous one was polar aprotic solvent, right? It is a polar protic solvent. So first the carbocation formation will take place, right? Because it will follow the SN1 pathway. It is weak nucleophile, poor nucleophile and weak base. So carbocation, after the carbocation formation, there are two ways to do the reaction. The first way is that the nucleophile will attack from any side, either front side or from back side, to get these two resulting products, right? So we will get these two products by SN1 pathway. The other way is that it will undergo a even elimination reaction. Even elimination reaction will be done here by an abstraction of this proton, and the double bond formation will take place here. So either it can be done by this proton, it can be the base can abstract this proton, or it can abstract the this proton. So according to the abstraction, depending on the abstraction, we will get the two products here. This is hydrogen only. Okay. But when it will follow the SN1 mechanism, again we will get the two product. One is from front side attack and one is back side attack. So we will get the two different product, pair of enantiomers, and here we will get the even products. One is Serzup and other one is Hoffman. So the always the Serzup one will be major one. Major one, and this is the minor one. Okay, it will follow the Markovnikov rule. So these four are products possible by the second reaction condition, that is under the methanol. Okay, so I hope all of you are clear with all these examples. So any doubt, any question regarding this session, you can ask me in the next class, and you can give your valuable feedback also. Thank you so much for your kind attention.